Bonjour, bonjour! Welcome to our next lesson on Faraday's and Lenz's law. So if you can please quickly title and date for me, and then we shall crack on with the notes before zooming later to do our summary questions from the textbook. So first thing is, thought I'd introduce you to this guy. He's a bit creepy looking, but his name is Michael Faraday, and he was an incredible physicist. He was the person who discovered the principle of electromagnetic induction. If you remember, we looked at that last lesson, so the idea that you can create electricity through magnetism. Absolutely incredible, and he made the first ever electric generator. Don't worry, you won't be quizzed about his life history in your exam. Actually, now you're not having an exam, so you definitely won't be quizzed about it. But yeah, so there you go, that was Michael Faraday. His law, the magnitude of the induced EMF, so this, as we say, is about creating that electricity in a wire, inducing electricity in a wire. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Now, last lesson we said that EMF was created when magnetic flux changed. Still true. But now we're saying, okay, how much EMF are we inducing? And the way we know that is you look at how quickly that magnetic flux is changing. Now, the reason I put magnetic flux linkage in there is that if you remember from GCSE, if you want to create more electricity, more voltage, more potential difference, you want to add more turns of wire. So if you have magnetic flux linkage is better to say because it takes into account those number of turns of wire as well. So this bit at the bottom is not an equation because you'll notice there isn't an equal symbol. However, there is a directly proportional to. So on the left you've got EMF, and it says it's directly proportional to the change in magnetic flux linkage over the change in time. So the faster you change it, the more EMF you produce. This is the reason, if you remember last time I showed you two graphs, I said that if you had a generator and you turned it slowly, you'd end up with something that looks like this. It's got a low frequency and a low amplitude. But if you take the same generator and you turn it quicker, you will not only increase the frequency, but you will also increase the amplitude. And the reason for that is that when you rotate it quicker, you are increasing the rate at which the magnetic flux linkage is changing, hence why you get more EMF induced. So that's Faraday's law. Lovely, we know that they're proportional to each other. Bit useless when it comes to questions. We want an actual equation. So in order to turn it into an equation, we go on to Lenz's law. So Lenz basically says the direction of the induced EMF or current is always such as to oppose the change producing it. Now you're probably thinking, what? Excuse me? We can show Lenz's law in the form of a minus symbol in this equation. But where that actually comes from is you have energy, and in classical physics, which is where this sits, so we're not in relativistic physics here, we're in classical, you cannot create or destroy energy. I know we've done the quantum bits, I know we've done that, so just to put that out of your head, we're in classical. You cannot create or destroy energy. So if you are going to create energy in the form of electricity, that has got to come from somewhere. And where it comes from is the force that you are applying to the magnet or to the coil when you are turning it. So when you are putting energy into turning the coil or magnet, you get energy out in the form of electricity. Lovely. Now, if you created electricity and that electricity then helps you to turn the magnet and it became this perpetual motion thing, you're not putting any energy in. Any energy. They were the words I was trying to get out. You're not putting any energy in. So you are therefore creating your own source of energy. And we know that can't be true. So he said, if you are getting energy out, so let's say you were putting a magnet into a coil, okay? That would create a current in the coil. We know that. Every current flowing through a wire has its own magnetic field. So the magnetic field would be created in a coil as well. So now you've got a magnetic field of the bar magnet, but you've also got a magnetic field of the coil. Now, if that magnetic field of the coil was such to attract the magnet in, it would be doing the work for you. And that's what I meant about not creating you are then creating energy. However, what actually happens is the magnetic field of the coil is created so it repels the magnet that is trying to come into it. So you, as the person pushing the magnet in, you have to do more work. Remember, work done, type of energy. So you are putting work in to get electricity out. If, however, you decided to pull the magnet away now, rather than pushing it towards, the magnetic field of the coil would switch. Suddenly, it will try and attract that magnet. And again, you as the person pulling the magnet away are then going to have to do work to overcome that magnetic field. Therefore, you're putting energy in and it's getting energy out. So as I say, fairly complicated explanation, but all that really happens is that in the equation, you now have a minus symbol. So going on a little bit further than that, the last bit is I'm just going to use that idea in what direction are currents. Can you please have a look at the top diagram? Moving a south pole towards the coil will induce a south pole to be created in the coil. And that means they repel the south pole nearing it. So the top one, where you've got a south pole moving towards, the coil will create a magnetic field to repel the magnet. The bottom one, where you are having a south pole being moved away, suddenly a north pole is created, which tries to attract. So you can see the magnetic field there has switched. If you look carefully at the arrows on those two diagrams, you will also see that the current direction has switched as well. So a south pole in the coil creates a clockwise current. A north pole creates an anti-clockwise current. And the way I know this is look at this bottom diagram here. It's a really, really simple way, but if you look at a coil, if the current is going clockwise, it is a south pole. And I know that because I draw an S and I add arrows onto the ends, and you can see that they are going in a clockwise direction. If the current is going anti-clockwise, it is a north pole. And again, if you have a look, if you draw an N and you add arrows onto the N, you can see they point in an anti-clockwise direction. So what they may ask you to do is say, okay, here's the situation. We've got a magnet being pushed in. What pole is created? What direction does the current go? And let's go through some practice questions now. So here we have question number 1, draw the direction of the induced current. Now here you've got a coil, you've got a magnet, but it is not moving. Therefore there is, helps if how do I write on pages? Help me. There's got to be a way of writing, press edit, that'd be the helpful thing. There you go. No, I don't want to. Oh, I hate this thing. Yep, lovely. Yes, that's the one. Thank you very much. See why? Let's delete this. Okay. What we're going to do? We're going to screenshot it. Then I can write on it. Okay, lovely. Right. Apologies for that. Let's carry on. Number 1, draw the direction of the induced current. There is no movement. You can see because it says V equals 0, which means there is no current. So that was a bit of a trick question. Number 2, draw the direction of the induced current. So first thing to notice is that you have a north pole being pushed towards. Now that means that this will become a north pole as well, because it is going to try and repel. So I make something like that, repel. And then if you remember, north is anti-clockwise, so it'll be going up and over, up and over. And that's my direction of my current. 3, draw the direction of the induced current. So here you can see the north pole is being pulled apart. So it's going to try and attract, goodness me, which means it's a south pole. And again, south pole is clockwise, which means the current here will be going up. It is clockwise as you look at the coil, by the way. Right, number 4, draw the direction of the induced current. You've got a south pole being pulled apart. So it is going to try and attract, which means it's going to be a north pole. North pole is anti-clockwise, which means it will be going down. All right, I hope that makes sense. join me on Zoom and we shall do some questions on page 199 of the textbook. Thanks everyone.